Okay, so yeah, time for some more QOI image format parsing stuff. Uh, I'm almost at the stage where I'm ready to where I'm ready to start writing a decoder for this in Zig. Last time we went through a couple of examples, just literally looking at the raw bytes of a QOI file and figuring out how this format works. I just want to do one more example before I start writing a parser for this. But I think things should kind of be straightforward. Okay. Yeah, so I think in the examples we created last time, we saw a couple of these appear. We saw this series of bytes appear. We saw diffs. We saw an index, although we didn't. There's an index in here, although we haven't calculated it. But I don't remember seeing this Luma example. And so I want to create one example where we see most of these things happening. And then after that, I think I'm going to feel confident to start writing a parser. Okay, so we can make examples like we did last time in this very simple way, where we're just going to create some basic a 3x3 image with some basic. Okay, let's make it like a 3x4 image. Give this some simple colors. One thing we didn't try out last time was also experimenting with alpha values. So I want to try and make an example that does this too. Because I'm pretty sure that as soon as the alpha changes, you need to just say this is a new byte, which means that there's kind of no way to compress like slight changes in alpha, which seems a bit weird, but given that most images have a fixed alpha, perhaps this is not surprising. Okay, yeah, but let's get to doing painting stuff. How does this work again? Is this currently too small? It is. Okay. Yeah, so let's start off with red as usual. So this itself should give, we should see some like difference and then some repeating units. Let's keep in this transparent alpha block. Let's then change to red again. This should use the index chunk. Then we can say change to let's try and change to something that uses this Luma one. So for this Luma, we need a relative change in the red and blue that that's what I guess using like 16 possible values, and then the green here. So what should we do that with? So we want some change in the green. Maybe we change the green by like 16 and then the blue by maybe by 3. And then yeah, this should be enough that we do pick up the change, but not so much. Okay, and then what else can we test out? I want to just do a couple more of these index examples. So let's go to blue. Okay, green's fine. And then let's kind of alternate between, let's do a dark gray, something that's very different. then alternate between this and the red. And then, what was it, 666. Okay, and then yeah, if we can read and understand what's happening in this scenario, I'll be happy to write the decoder. Okay. So why don't we just call this like the 3x4 PNG. Let's convert this magic K 3x4 to the QOI, and yeah, let's open this up. 3x4 QOI in the Hexel mode. Okay. So yeah, let's annotate this. So let's do like 3x4 annotation. And yeah, I just want to confirm that the way I'm thinking this works in my head is actually working in reality. Okay, so yeah, these first 4 bytes are just this magic bytes. This is then the width, which is 4, and the height, which is 3, as expected. Let's actually bring up a photo of a reminder of what this is. Like annoyingly, only when you're actually resizing the image does it display in ifran view. But there's a way around that. What is it? It's like snipping tool. Okay, this will be our reference, and so we can move it up here or something. Okay. And then yeah, the 4 here, the 4 byte represents what it's like RGBA, and yeah, we do have an alpha here as expected, and then the 0 corresponds to some linear color space. Okay. So then at this point is where all of the color information begins. So we start off with the byte 5A, which is in binary 0101. A is 10, so this. And yeah, what is this? So the first 2 bytes, the first 2 bits is 0, 1. That corresponds to this byte diff. And then the DR values here are equal to what? 1, 2, and 2. But we need to do the appropriate offset. And so this QOI array is actually -2, -1, 0, and 1. So these actually represent indices of this array. So actually these offsets, and before we start this, we're keeping a running track of all of the pixels. So the current pixels begin with 000255. Okay, and then we're going to apply a difference transformation to these numbers. So 1, 2, 2 represent the indices -1, 0, and 0. So when we add -1, 0, 0 to all of these, we end up with 255, 0, and 0, which corresponds to the red pixel. That's right, can't put red, as expected in here. So then the red pixels are repeated 2 times, which means that I would expect to see a this run byte here. And what do we get? After the 5A, we see a C1. C is 12 in binary, so 1100, and the 1 is just, of course, that. So the first 2 bits are indeed this operation run. And here then the run value is equal to a 1. Hey, even in 2-step. Yeah, I'm just doing one more final example before I start writing the decoder. Mainly because we did some calculations for the hash last time, but I didn't actually verify it. And so in this example, I can just verify that that's going correct. And likewise, that changes in alpha values, you just use this. But, yeah, we'll see. So yeah, so this run here is 1, but all of these runs are offset, so we need to add in a 1 to this. So then we do 1 plus, which then gives us a 2. So then we have 2 of the same pixels repeated after one another, which is what we expect. There's then suddenly a feed, a 0 opacity pixel. So I'm expecting then to see this happen, but with kind of 0 byte at the end. So yeah, we've done 5AC1, so now we're off to 0, 0. I know, verify assumptions before coding. One of the aims of this is for me to actually understand this format, and by doing this example, I will understand it more than if I just straight up code this. And also, if I straight up code this and there's bugs, I can see myself spending 3 hours trying to debug that when I don't actually understand what's going on, as opposed to understand this first and then reducing the bug time. But now I'm kind of confused in that we're seeing a 0, 0 byte here and it's not this. So what's happening? Oh, we're seeing an index. Okay. Interesting. Okay. I mean, this is why I'm doing this. Unexpected things happening. So now this is an index, and what is this the index of? The index is, well, 0. So, oh yeah, chat 2-step says, Chad demands that you blindly code in circles for our entertainment. Yeah, that would be entertaining for you. Not exactly for me at this moment in time. So I think if this index is 0, perhaps this just means that when this running array is, I guess it does say 0 initialized. It's just referencing the very first part of this array. Yeah, I suppose the hash of this kind of 0 pixel is going to be, this isn't zoomed in enough, is going to be 0, so yeah, so I guess this is fine then. Curious, and then we end up with, we should end up with that pixel. Okay. But then we end up with 32, which is 0011, 0010. So the first 2 bytes are 0, so this is again an index, which we would expect since we're going back to red now. So now we're gonna have to do this hash calculation stuff. So I'll just say like of index. Okay, and what's the index here? The index is okay, 3 times 16, so 48 plus the 2. So we end up with 50. And is this what we got for the red? I'm pretty sure from last time when we did the calculation, the answer was yes. Where was this annotation? Was it this one? Yeah. When we hashed the pixel, when we hashed the red pixel, we got 50. Great. I should copy this. Okay. Great. So yeah. So then we've recovered the red. So it's that again. And then what? Now we've changed the color slightly, so we're expecting a difference key. And yeah, we see FE here, and FE is what? 0, 1111, 1110. So the first 2 bits are, oh, okay, something unexpected has happened. The first 2 bits are 1, so we're not actually yet seeing a diff. We're seeing possibly a run. No. We're seeing this one. A completely new specified number. Right, which is what we entered in. What we entered when we chose the key for this. So yeah, I'm kind of surprised that this Luma option didn't activate. Like, why not? I mean, this is a shorter number of bytes. I would have assumed this is what happened. Oh, I think it's because I changed this value by 16, which is actually too large a change. Oh yeah, it's in here. The change can only be between 8 and 7. Oh damn. Let's change this example a bit. Because I really want to. I just want to see this. Let's open up this 3x4 example again. And now in the brushes. Okay, well, so we want to change. Well, no, hang on. The we changed the green value by 10, and so that actually should be fine. Like, everything should have been within the limits. What's going on? Oh. Like, the red value is unchanged, so that's a 0. The green value is 16. Oh, it's the relative difference between them that can't be more than, the relative difference needs to be between 8 and 7. Okay. So we change this by 16, which is totally fine here, but then the value here is going to be the difference in red, which is 0 minus 16, so it goes out of the limit. Okay. So if we do want to do something that activates this, we need to change the green a bit, but then subtly change the red and the blue to be of a similar difference as well. So what if we change the green by 10, like by 16, and then also the red and the blue by 16? Then those should, we'll do it by 15. Then those should cancel out. Okay, so let's I need to think about signs now. This is hard. Okay, so if we make everything a positive change, things should cancel out. So increase the green by 10, also increase the blue by almost 10, so let's make it 0 E instead, and then let's increase the FF here by like 14 or 15, so we could make this like 0 D instead. Okay. Okay, let's see if changing this pixel now results in, wait, was that really the color? Yeah, okay. Okay, we've saved that now. Let's re-export it. And then let's convert the buffer. No, what's happening? Okay, this looks, hopefully this is the new one. Yeah, we see this 5AC1 as usual. Yeah, the new, the index of the null pixel, the red one again. Okay, now we do see this difference here. Now we see this B0. Okay, this looks good. Okay, so instead of an FE here, it's now B0. Oh, okay, thanks Two-Step. You found a link to a bunch of QOI test images. This will be very important when we do the next part of this. So github.com /lab QOI issues 69. This one here. Okay, it's we can unpack this if necessary. Okay. Okay, this is good to know. So yeah, so B0B in is 11. So what? 0 1 0 1 0 and 1. And then 0. So this is what's this? We got it. we got this Luma tag now. Great. Okay. So now this is off Luma. So now we have the diff green is we have the diff green, the dr minus the dg, and then the, like, why is it, let's call this dg. The dg, dr minus dg, and then the db minus the dg. And so these are equal to 3, 0, and 0, which is not exactly what I expected. No, so something's very wrong. It's not just B0 here, it's, we need to take 2 bytes. So this is actually B0, 66. Okay, and then 6 is just 0, 1, 1, 0, 0, 0. Okay. Okay, so the first 6 bits are the DG, and then etc. So this is a change of what, 3 times 16, which is 48. Why does this seem wrong? And then the 6 and the 6. So yeah, what's happening here? So yeah, the green channel is used to indicate the general direction of the change, sure. And then, but no, we didn't change it by like 48 though. We didn't change it by this much. We just changed it by 16. So why are we getting 48? Yeah, this is a big change. Okay, maybe it's some. I mean, did I do something silly when I made this in Paint? No. Like if we open up this and then use this like eyedropper tool, where is it? This one. Can we see what this color is? I mean, that change looks like 16 to me. What's going on? Oh, no. Oh, I was. Okay, this B is an 11, which is this. Right, 8 plus 2 plus 1 is 11. Okay. In either case, we'll continue just with this other stuff, since it will maybe this will work out in some way. This is weird though. Okay, so okay, I think I understand it now. Since the green channel is going from -32 to 31, a change of +10 is actually like 32 plus, sorry, it's a change of 16, and so 16 plus the 32 gives the 48. Okay, there we go. Yeah, so we needed to do offsets. So then, so what we really need to say is, And this is why this is called a diff green, not DG. So, since the diff green is this 48, the DG is actually the diff green minus, or is this plus 32? Yeah, plus 32. No, what am I doing? I'm getting something wrong with signs. We want this to be 16, so we want to do 48 minus 32. So we wanted to say that the DG is equal to the diff green minus 32. Okay. Which gives us the 16, which is what we wanted. And so now we have that DG, we can now say that the DR is going to equal 6 plus the DG, which is plus like 22. Wait, I'm jumping ahead. Each of these come with offsets as well. So, okay, yeah, so it is the case that I think these number conventions are fine. I'm just getting a bit confused about this. Maybe, what does this stuff say? What does DRDG mean? Does that mean minus? We'll continue with this. So the DR here is the DG plus the 6, which is going to be the 22. And then likewise the DB is going to be the GG plus the 6 as well, which is 22. But now we need to do the offset stuff. So now we go, how is this offset working? So maybe actually these we first have to map these values to this stuff first and then apply it. Because right, from memory, these are meant to be similar to 16 as well, but not as large as 22. So okay. So this thing is equal to 6. So the actual, what am I doing? We just want to say like the DR minus the answer is this is meant to be like 6 plus 8. 6 plus negative 8, I think. And likewise, this one here should be the DB minus the DG, like this value minus the 8. So I'm going to put the 6 minus the 8. And we get negative 2 as well. Yeah, this whole part of this specification could be a bit clearer, I think. So then with all of these changes, the next pixel is now going to be the 255 minus the 2. Wait, were we actually getting this? I didn't think we were. So we ended with 55 and then I thought we did something different. Yeah, we got like we got something in the positive direction here. What is? Yeah, we're doing wrapping stuff. Yeah, we're gonna when we write a decoder for this, we're going to have to use wrapping operations. That's for sure. Oh, I think I understand the problem. I think these are still relative differences to DG, so I think I'm just meant to add each of these to the DG now. Okay, so then we can say this was like a mess. Okay. The DG difference is 10. The D red difference is now the 16 minus the 2. And then the difference in blue is also 14, the 16 minus the 2. Okay. So now when we add 14 to FF, we should end up with it's just the same as 13, which should be D. Okay, which is indeed what we have here. We're then adding the 16 to the 0. All of these are now in hex, by the way. And likewise, when we add the 14 to the 0, we also now we're just adding 14 to 0, which is E in hex. Okay. Okay, and this is a kind of like dark gray. Okay, we got through that, but now I actually know what's going on with this operation. Yeah, thank goodness I did this example and wasn't spending 3 hours debugging how this functionality works. Okay. So now we can move on from this part to the 8FB8. Okay, so this 8 is 0, 1, 0, 0, 1, 1, 1, 1. When something starts with, when something starts with 0, 1, it's this diff byte. So we just need to do the relative dr, dg, and db again. But okay, first of all, were we actually expecting this? So now we've got this white pixel. Like possibly we could get to it, but I'm kind of surprised that we can get to it from here. Have I missed something? B066. This seems to be fine. Okay. We'll continue with this. So this is then going to be 0, 3, and 3. But this is with the index notation, so actually this corresponds to -2, 1, and 1. Okay, so then we should end up with, really? 0D, this is all in hex, and 1, 1. No, this doesn't look like a white pixel. What's going on? If it was possible to zoom in all the way with Paint, I wouldn't have to switch through to these other apps. This is so anyway. Let's do this. I dropped tool again. This is not FF. Yeah, what's going on? Like we kind of see this. Like we see this 666 here for this gray pixel. The very end here, but and for the grey one, when it is FE, we are seeing this one. Oh, I see. So this is the value used when the alpha value remains unchanged. But this is what you do when you need to update the alpha. Okay, that's good to know. But yeah, it still leaves us with this part. So this C0 should be something like a run. Since there's two greens, like there's a repeated green. Yeah, so then why are we actually using 3 bytes to describe this gray pixel? Oh, I see. Noobish error. What is 8 in hexadecimal? Clearly it's equal to 4. Oops. Okay, so now that the 2 bits actually 1, 0, we're getting another Luma op. Curious. But okay, that's what it is. Okay, so more practice with all of this diff green stuff. So yeah, so the values are what? They are in the first field. Since it's op Luma, we need to look at the next byte. So it's 8FBA. Okay, B is 11, so that, and then the A is 10, so that. So then these values are going to be 15, but with the weird sign thing, and likewise 11 and 10. So now we need to do all of this translation stuff. So the DG is now going to be the 15 minus the 32, which is what, minus 17, I guess. And then the dr minus the DG value is going to be the 11 minus the offset, and what's this offset? The 8. 11 minus 8, which is 3, and likewise this difference here is going to be 10 minus the 8, which is the 2. Okay, so now actually applying all of these changes, we now have 0D is, we're off by 1 error in that, since the next pixel is wide, it should be FF, 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 and the 0D here is a like 13, so I kind of want this to be a minus 14 instead. What's happening? What is the problem? Did I do another bit conversion error? Yeah, this isn't what we want. So yeah, that's 8 and that's F. And what's going on? Like we checked this last time, but yeah, it is a 0D here, and then it goes into everything else. I'm not seeing it. What's wrong? Okay, so maybe this is off, but maybe thinking about these other values would help in some way. So the dr here is going to be like 3 plus 3 minus 17. Minus 13. No, but again, it's I'm expecting a minus 17 here. Oh, massive rookie error again. This is also late night error. These are describing the change in the green pixel. This is the red, so this is actually the one we want. Okay, everything's fine. It's totally fine. Yeah, 16 minus 17 does give us the 255. Okay, this is still another thing to remember when we're actually writing the decoder, that this is a subtlety. Okay, everything is fine. So yeah, so the DG is negative 17. The D here is a 13, but the 13 minus the 13 is 0, and we want 55. We want 255. I'm making another mistake somehow. I'm being silly. 3 minus 17 is minus 14. It is a really late night for me. And finally, the 2 minus the 17 is minus the 15, which will give us what we want. Great. Yeah, so now we end up with the 255. Let's keep this consistent. Now we end up with the FF, the FF, and the FF. Okay, which gives us the white pixel. Okay, we are nearly there. We are so close to being done. Okay, so now we end up with this 7B, and what's that? 0, 1, 1, 1. 11. So this is a difference. Do we expect a difference here? Yeah, we're going from like white to green, so white to bright green, so we do expect this. And here the differences are actually easy to calculate. So we've got 3, 2, and 3, but these represent indices, and that is, they actually represent 1, 0, and 1. Okay, so then when we add those to these values, we end up with FF plus 1, which is 0, FF plus 0, which is still 255, and then FF plus 1, which is 0 again, which is the green. Great. B. So now it's C0, which, like I predicted before, should be the repeat. So C0 is, C is 12, so 1100. But now we need to be a bit careful because a couple of bytes begin with 11. So we need to just check out the next 6 bytes and then compare if those 6 bytes are that or that, which they're not, which means it's a run. So therefore the unadjusted run is 0, but we actually need to add 1 to it to correct it. So then the run is 1. So then we repeat this pixel 1 more time, which is what we expect. Okay. Now we go to the hashing stuff, which is really important to check out. So now we see this new gray pixel, red and gray. So we now expect a new pixel after C0, which you can see what it is here, all of these 6. So we have FE 66, 66, 66. And so the F is 111 0, and then all of the, I'm just like totally switching between notation, but that's fine. This begins with 1 1, so we need to compare all of these, but it's FE, which means it's this one. So now it's op RGB, and yeah, so then we just specify what the colors are immediately. So now in hex it's 6x, 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 and then still the FF, which is the kind of the gray. After this, we end up with a 32. Yeah, so what's this going to be? This is 0, 0, 1, 1. So it's a double 0, so it's another index. So now we need to do the index calculation. So now the index is literally just okay, 48 plus 2. So this is just the red that we calculated before, which is the case. Great. And then we'll likely get another index, but actually we needed to calculate the hash of the gray just to make sure that worked. Okay. So yeah, so we get this gray. How do we do the hash function? We have to do this thing. So let's make sure we hash this. So the hash is equal to like 66 in hex, which is what is this? 6 times 16 plus 6, and I don't care. I don't want to do that in my head. 102. So now it's 102 times 3 plus 102 times 5 plus 102 times 7 plus 255 times 11. And then from basic algebra, this is just the same as 102 times 15 plus 255 times 11. And we actually need to quotient all of this by, take the remainder of this by 64. Okay, so what's this? Now it's 102 times 15 plus 255 times 11. No. Like this, yeah, we'll just do it. Now let's just subtract this in a simple, oh come on. Subtract this in a simple way. Minus 640, enter, 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 minus 64. So then we end up with 53 as our hash. Hopefully this works. Let's see. So yeah, so we got the red here for the 32, and now we end up with 2F. So 2F is 00101111. So this is another index, and the index is now, oh no, we're getting something less than 48. So something was wrong with the calculation. Oh, whatever. It's basically right. So this should be 32 plus 15, which is 47. So do I want to redo this calculation to try and recover 47. No, I just want to believe this is true, but I feel like I should. Okay, so we're doing... Yeah, like what's wrong? And then we're just adding and then we're just subtracting this several times and then this several times. Okay, I got the right answer that time. That is enough for me. Don't know exactly what happened. Great, so it's, the index is this, which means it's the gray. And then we're done. We've now covered the 14 pixels, and so the rest of this must be filler. Great, okay. Let's save this, this annotations. So this is the 3x4 QOI, and we added in, what is this file called? 3x4 annotations. Yeah, so now we can just say git commit. Did another example which used the Luma op, and what was the other one we did? Just like the op RGB, I guess. Well, it also had, did we have RGBA in here? No, the RGBA one was actually just the zero index. Okay. And I don't mind doing git pull, like, nothing's, the only place I'm changing stuff is from this computer. It's past midnight, so I kind of actually want to go to bed now, but this hour has been informative. I was happy I was happy we did this example. This stuff wasn't at all really clear what was going on, especially since there's like offsets within offsets, like, yeah, let's just, how does this work again? So the number in here, first of all, needs to be offset. Each of these represents something between -8 and 7. So you need to subtract 8 from each of these. And then those give you the kind of true difference values. And then likewise this one here, you need to -32. Okay, and then, okay, so after all of these offsets, you then actually get the true relative numbers, and then you just need to, you either keep the true one, or you do some further changes, and then you add that to everything again. Okay. And then, yeah, likewise, and then one of the subtleties with these two was that you use this one if the alpha doesn't change. But if the alpha has changed, you do that. And then also, since the running array is 0 initialized, it means that like an empty pixel where every value of 0 is in here and does have an index of 0. And so you can reference that with literally just the 0 op. Like, yeah, when the 0 appears, it was after the C1. Yeah, this 0 here just represented the null pixel, which is actually useful. Yeah, instead of having to just use up 4 bytes to specify something blank, you just, in the very beginning, you can just use 0. Okay. Yeah, okay. Yeah, I think I'm gonna call it now for tonight. But tomorrow is the weekend, and so tomorrow, I can spend possibly, hopefully it won't take an entire day, but we can spend a significant part of the day now basically kind of automating this and producing an array the actual of the actual pixel values. And then once that's done, I'm going to be really happy both in this project and future projects working with images, because then I'll have code which, since I write it, it will be relatively simple and it will be very straightforward. Yeah, I won't need to rely on some of the library. It would just be like 100 or 200 lines of code. And a more advanced feature is that I think like this is structured in such a way that this decoding can be done in like almost a it can't I wanted to say it could be done in a multi-threaded way, but I don't think it can because of this running array stuff. There was something about this that was like multi-threading though, from some video I had seen. What was it? Something to think about next time. But yeah, thanks for joining again, Two Step, and yeah, hopefully I'll see you next time or whenever that may be. But yeah, have a good night. Bye.